You've probably seen that random bit of trivia floating around the internet claiming human bone is actually stronger than concrete. It sounds like one of those exaggerated myths, right? Well, we're going to put that exact claim to the test. We're putting human biology head-to-head against modern engineering to see how they really stack up from the moment they're built to the moment they break.
So, let's address the rumors right out of the gate. Are our skeletons honestly outperforming the literal foundation of modern human civilization? When you look at the actual data from materials science, you realize pretty quickly this isn't just internet hype. It's engineering reality. But to see exactly why that is, we need to look at the numbers.
The trick here is that we can't just look at absolute bulk strength. We have to look at specific strength, which is basically the strength-to-weight ratio. Our bodies just can't afford to lug around massive, heavy skeletons, so bone evolved to be incredibly efficient. Pound for pound, cortical bone, which is that dense outer shell of your skeleton, is about 8.5 times stronger than standard concrete when it's compressed. And when it comes to tension, meaning pulling forces, bone is a massive 57 times stronger. To figure out how bone pulls off this massive advantage, we're going to trace the material life cycle of both. We'll look at their ingredients, how they handle daily physical stress, what happens when they finally hit their breaking point, and then how they repair themselves. Let's start with the ingredients. Concrete is essentially a messy, random mix. You throw cement, water, sand, and chunks of gravel into a mixer, let it cure, and, well, you get what you get. Bone, on the other hand, is built like a hyper-organized biological cable. It uses a 7-layer design, starting all the way down at the microscopic level with collagen proteins and mineral crystals, which are intricately bundled up layer by layer into the skeleton you're using right now. Because concrete is just this random mix of stuff, it introduces a pretty huge structural flaw. When you throw random rocks into cement, it creates weak borders around those rocks called the interfacial transition zone, or ITZ. Because it's totally unorganized, this zone is highly porous and weak. Under pressure, it's essentially just waiting to crack. It's the exact spot where a structural failure is born. Now compare that messy border to how bone handles its internal structure. Bone is made up of tiny pillars called osteons, and they're wrapped in what's known as a cement line. But instead of being a weak, porous mess like we saw in the concrete, evolution specifically engineered this border to act like a defensive wall. When a microcrack starts forming, this boundary is perfectly tuned to physically bounce and redirect the damage away. Moving on to stage 2, daily stress. Standard concrete is isotropic. That's just a fancy engineering term meaning it handles weight the exact same way from all sides. It's totally predictable, and that's great for pouring a sidewalk, but it's highly inefficient. Bone is anisotropic. It physically adapts and aligns its strength to push back against the forces you experience most often, like gravity or the constant pulling of your own muscles. Because of this, bone focuses its strength exactly where you need it. Straight up and down your leg, for example, your bone can handle a massive 135 megapascals of pulling stress. But since it's anisotropic, if you apply force from a weird angle, that strength drops off a cliff. If a twisting force hits your leg from the side, exploiting those weaker angles, well, that's exactly why people suffer those nasty spiral fractures. Bone also has a pretty wild trick for dealing with stress called viscoelasticity. Concrete acts the exact same whether you push it slowly or hit it really fast, but bone dynamically shifts its physical properties depending on the speed of the impact. Simply put, your skeleton literally behaves differently when you're standing still compared to when you're suddenly sprinting. If you take a fast impact, like a hard fall or a sudden jump, that rapid speed forces your bone to instantly stiffen up. It actually boosts its own strength on the fly to handle that sudden spike in kinetic energy. But there is a trade-off here. By stiffening up, it loses its flex. So if the impact energy pushes past that newly elevated limit, the bone risks shattering entirely rather than just bending. While we're on the topic of movement, bone also acts as a built-in shock absorber. It has this rating called a loss tangent that makes it incredibly good at taking mechanical energy and just diffusing it. It literally dampens the high-frequency vibrations traveling up your legs every time you take a step. This protects your delicate joints, your spine, and keeps your brain from getting completely rattled inside your skull. All right, stage 3, the breaking point. This is where we measure damage tolerance, also known as fracture toughness. Basically, how much energy does it take for a tiny microscopic flaw to turn into a complete structural collapse?
Concrete is notoriously bad at this, maxing out at a toughness rating around 1.4. Cortical bone reaches up to 6.4, and that superior tolerance comes straight from that 7-layer design we talked about earlier.
The absolute easiest way to understand this difference is by looking at their R-curves, or crack resistance curves. Concrete has a flat R-curve. Once a crack starts, it spreads rapidly, and the material basically just gives up. Bone, though, has a rising R-curve. As a crack grows, bone actively fights back, meaning the material actually becomes harder to break the further the crack goes.
Here's the exact playbook for how bone fights back. First, down at the microscopic level, proteins act like tiny biological glues, physically snapping their own molecular bonds just to absorb the impact energy. If the crack keeps going, it hits those stiff cement lines we mentioned, which physically twist and deflect the crack off its path. And finally, uncracked pieces of bone will actually bridge the gap behind the crack, literally squeezing it shut.
Which brings us to the final stage, repair. When concrete gets damaged from heavy loads or weather, those micro cracks just sit there. Water gets in, it rusts the steel rebar, and the structure degrades until we have to spend billions of dollars patching it. Bone, however, is constantly running its own self-healing program in the background, fixing microscopic damage on the fly before you even know it's there.
You can think of this cellular repair process exactly like an active construction site. First, cells called osteocytes act as the site supervisors, sensing the stress from a microcrack. They call in the demo crew, osteoclasts, which use acid to dissolve and clear out the broken rubble. Right behind them are the osteoblasts. These are the builders, pouring a fresh organic matrix that quickly hardens and restores the structure perfectly. This biological blueprint is just so efficient. In fact, it's so good that structural engineers are currently pivoting hard into biomimicry. They are desperately trying to copy this exact cellular process to save our crumbling global infrastructure by creating something called autonomous self-healing concrete. Now, traditional concrete does have a tiny bit of natural healing, but it's structurally negligible. The new experimental biomimetic mixes use a crazy process called microbiologically induced calcite precipitation. Basically, during construction, they embed dormant bacteria and a food source, like calcium lactate, straight into the wet concrete mix.
Here's how this sci-fi material actually works in practice. When the concrete eventually fractures, the crack physically breaks open those embedded microcapsules. Atmospheric moisture and oxygen rush in, waking up the dormant bacteria. They immediately get to work feeding, and they essentially create solid limestone directly into the void. It literally heals the building, bridging the crack and sealing out corrosion, just like the builders in your skeleton.
So this entire showdown really highlights a massive shift in how we think about engineering. For centuries, we've built our world with brute force and static, heavy mass. But if millions of years of evolution perfected the ultimate damage-tolerant, self-healing building material right inside our own bodies, what happens when we finally figure out how to scale that biological blueprint to build our cities? Because that right there is the real future of human architecture.
What the fact? Follow for more.